The main event here we have Professor Valentin Artroll giving us a fabulous conversation named The Youngest Ocean on the Planet, the Making of the Atlantic Ocean. So without further ado, ladies and gentlemen, please help me by welcoming Professor Valentin Troll to the stage and enjoy.
Thank you so much. As always, it's a great pleasure being here. And I'm particularly grateful that you have chosen me over the pool party. So thank you. I'd like to talk a little bit about the Atlantic Ocean today because we have a sea day ahead and we're going to be sailing the Atlantic Ocean. So it's quite fitting, I thought. And well, what most people don't know is the Atlantic is actually a bit of a youngster when it comes to oceans. It's the youngest of all the oceans. So it hasn't actually fully grown up. And I explain what I mean a little bit later in the presentation. So, but a few facts to start with. It's the second largest ocean despite its young age. It covers about 20% of the Earth's surface and it contains about 29% of the Earth's surface water. The Atlantic Ocean is of course going all the way from, well, the north of the planet to the south, and inside the ocean we have a mountain range underwater, and it's the Mid-Atlantic Ridge. It's thousands and thousands of kilometers of a submarine mountain range. And again, I'll talk a little bit more about this in just a short while. So here is that mountain range, and it's like a spine that runs through the Atlantic. And well, you can also see the continents. They're a bit like a jigsaw puzzle, and people have over 100 years ago realized you could actually fit them together. And the spine is where the ocean is separating and actually growing. But more on this in a few seconds. The Atlantic Ocean, as I said, is the second largest. And well, to give you a flavor, the United States is less than 1/6 of the size of the Atlantic. And the Atlantic started to form in the Jurassic era. That's when the dinosaurs roamed. That was about 180 to 150 million years ago. This is where the Atlantic started to form. And it actually started to form from the south towards the north, like a sip. It unzipped, and this is quite fascinating. I find that continents break apart like a sip, and we have evidence for this, and this goes back to this gentleman here. This is Alfred Wegener, and he came up with this idea that you could fit all these continents together, and he collected evidence for this. And when he put his jigsaw together, he realized that there are certain things that go across these boundaries. Certain fossils can be matched up, and like in a jigsaw, he could find motifs that would actually fit, or certain volcanic rocks would fit if you put them together in the right way. And this way, he reconstructed a supercontinent, the supercontinent Pangaea. Pangaea, all Earth. And he postulated that sometime prior to the Jurassic, we must have had this supercontinent where all the continental masses were together. And in the little inset just next to his picture there I'm showing some fossil provinces. And it's a little small, but there are certain fossils or fossil groups that would actually be found across some of these boundaries. And that enabled him to put this together and make it work. He got a lot of criticism at the time. He was called all sorts of names. And one of the major criticism was he didn't have a mechanism that allowed him to actually move these plates apart. We have learned a lot since those days, and he has been fully accredited. In the 1960s, people realized there is a mechanism, and that is seafloor spreading. He didn't have a better name. He called it continental drift, but it's actually not quite right. It's not the continents that drift. It's the seafloor that breaks apart, and it spreads ever so slightly. The Atlantic spreads at about 2 centimeters a year, and over millions of years, well, this makes a big basin. It makes the ocean. And we know this because we can actually date the age of the ocean floor. And here we have in gray the continental masses on the right-hand side, and in color the age of the ocean floor. 0 being in bright red, being very young and hot, and the blue colors are much, much older. There is no blue colors in the Atlantic. We don't have rocks of that age, and this is why we can actually say it's a very young ocean, because it doesn't go in terms of age beyond the Jurassic. Then most of the ocean floor then gets younger the further we go away from this central spine, from this spinal cord, and that tells us very clearly that's where the rocks of the ocean floor are actually produced. And when you go down there with all sorts of devices these days, we have submersibles, you can map the ocean floor in detail, also with remote methods. And what we found is that the ocean floor has stripes. They're not visible in terms of color, but they're magnetic stripes. The Earth magnetic field, it flips over every so often, and when it flips over, well, the tiny little needles, the iron-rich needles inside the lava that forms, they start to feel the magnetic field and they orient accordingly. So, and when the Earth magnetic field flips from negative to positive, then the needles will show that. So rock formed at a certain time reflects the polarity of the Earth magnetic field, and that gives stripes. Depending on how frequently it flips, that's defining the width of those stripes. So, and this is what we see all along the ocean floor, and we see that in the Pacific as well. It's not unique to the Atlantic, and it allows us to postulate that the plates are spreading at these mid-ocean ridges, this spinal cord that runs through many of our world's oceans. So, when we look at the little diagram here on the top right, let's see whether I get this, yes. So here's our ridge, but then of course the question is, well, unavoidable. What happens to all that material? If all the oceans would spread all the time, then the planet would grow, but we know the Earth doesn't really change its size or its shape very much over known geological time. So the answer is we are actually destroying ocean crust in many places of the world. Mature oceans, they subduct ocean plates when they are cold and old, then they go back into the mantle and they get recycled. And we shall have a look at whether this is the case in the Atlantic as well, but a little later. Let's talk about this rifting a little more, this spreading of plates. It's really intriguing, isn't it? And geologists, they look for analogs. They want to see situations where we can see the process in action, because the present is the key to the past, as we argue. So when we see it in the present day happening, then likely it must have happened in the past. So, and indeed, we see various stages of spreading. In East Africa, it's a very young spreading system. Likely we'll make an ocean there in the future. But it just about started. There's a few volcanoes there, and there's the Rift Valley. Well, this is actually where humans originate, in that Rift Valley, a sheltered little valley in East Africa. When we look at the process a little further, the Red Sea is actually an example where the spreading has gone a little further, a narrow, long sea, and this is underlain by a spreading center. And then, of course, once we're spreading properly, once we have a full ocean, then the Atlantic is a good example. Do we know more about this? Well, we can go to Iceland, because Iceland is peculiar and fascinating at the same time, because Iceland is one of those places in the Atlantic where the spreading center is above the water. And the two images at the bottom here are from Iceland. There we see these large fractures running through the entire country. This is where we have the North American plate on the one side and the Eurasian plate on the other side. And this is where the drift of these plates is actually happening. So here's a few more impressions, and it's a large-scale feature. And if you are visiting Reykjavik, this is a place to go if you have an opportunity. And why is Iceland above the ocean and not like the rest of the mid-Atlantic ridge below the ocean? Well, I mentioned it in my first presentation. It's because there's this melting anomaly that's pushing everything up and making extra many volcanoes at the surface. There's a plume underneath. Very similar to Hawaii. Hawaii also has one of those plumes or hotspots underneath. It's a bit like in your soup pan when you have bubbles coming up in one particular place. That's like a hot spot. This is a central point where hot material rises up. It's not necessarily linked to spreading. It's an anomaly in the mantle, and this comes up at Iceland, and this allows us to see the spreading center, which is a really unique geological situation and therefore highly fascinating. A few more impressions. So this is the Thingvellir Valley. This is where the Icelandic Parliament was introduced, and as I said, if you have a chance, it's quite a spectacular place. And if you travel along this valley towards the ocean, at some point you'll see water in the valley, and of course it continues underwater. If you're a diver, you can actually get your gear on and can dive under the water, and you can dive inside these fracture zones under the water. So here it moves from an onshore rifting system into a submarine rifting system. So this is really where we are seeing the submarine spreading system in action. And if you're really bold, you can go quite deep. But these are not my images, I must admit. So, and talking about depth, I should mention that there is various depth ranges in the Atlantic as well. And we've just moved from Iceland into the ocean, and the ridge system is pretty tall actually. But the deepest point in the Atlantic Ocean is actually at 8,600 meters, and it's off Puerto Rico. And usually the average depth of the ocean, the Atlantic Ocean, is about 3,300 meters. And of course, this mountain chain under the ocean, it's at about 2.5 kilometers depth. And the little inset in the lower left gives you a flavor of that. So there's a really deep place, and I'll come back to this in a few minutes, because there's a reason why it's so deep. But how do we know all these things? How do we know what's going on down there? And here I wanted to kind of give you a flavor of my days on research ships. And there are several research ships I sailed on. And usually this presentation is given when we're out on the ocean on a sea day. And usually it tends to be terrible weather. So, I have these two images to make travelers feel better, where I had some really stormy days out on the ocean. So, anything you have seen on this ship is luxury compared to these research ships, I tell you. So. But these research ships, of course, they are very useful because they have all sorts of devices. We throw buckets overboard, steel buckets, and they can scrape the ocean floor and we get samples. But we can also have submersibles launched from these research ships that go down. And these days, the submersibles even have arms. You can actually grab samples. Well, every now and then, it's a bit of a fight to get the sample off because it can't hammer, so it can only grab. So it's not always straightforward. Every now and then, you lose a piece as well of the submersible, unfortunately. And this is not so well liked by the captain. I remember, anyway, let's not go there. So, and what we see down there with the submersibles, the image on the top right, you see the arm of a submersible and a lava tongue coming out. But there's a lot of fractures and fissures down there. As we've seen on Iceland, this continues at depth, and these fractures and fissures are not dissimilar to the ones we see in Iceland. Here is the 22 eruption in Meradalia on the Reykjanes Peninsula, and you see it's a wall of fire coming up, a wall of lava. It's a fissure, actually, that gives rise to these eruptions. So a lot of fractures, a lot of fissures. And here's one of them. And, well, at some point, the light is insufficient, and you can't quite see all the way down. And that implies it's a deep fissure. It goes down for quite a while. So this is how we picture this. There's fracture systems in this valley, and this rift valley here is breaking apart, and this spreading allows magma to well up, and then it becomes lava that fills the rift valley ever so often. So here's a few impressions, and I showed this image before. There we have fresh lava coming out, but of course it interacts with the seawater almost immediately, and it quenches against the seawater. But the interior of such a tongue is is liquid and it continues to flow and it makes these tube-like features. And I'll say a few more words about this soon. On the right-hand side, I'm showing two strange phenomena, quite frequent actually, inside the Rift Valley, and that is white and black smokers. This is not smoke, of course. This is actually geothermal waters that are coming up. They're hot and they have a lot of dissolved minerals in them. When the hot, acidic fluids come out and they meet the usually alkaline and cold seawater, they start to lose all their mineral components. They precipitate as tiny little needles, but from a distance it looks like a haze, like a smoke. And I'll come back to that later as well. This is actually one of the main phenomena that produces ore deposits at the ocean floor. And this is why people are very excited about going down to the ocean floor now and trying to harvest these minerals there. They're forming as part of the volcanic activity along the mid-ocean ridges in form of these smokers. And the different color comes from different minerals, maybe not so complicated then. The white ones is more silica rich and the dark ones is more copper and sulfur rich. So I mentioned the tubes that form when we have lava flowing at the ocean floor, and here's a few of those images taken from submersibles. We also sometimes have ropey lava and these lava layers or lava lakes, as we see in the layering in the B image in top. So this is from several kilometers down in the Rift Valley in the Atlantic. So here's a few more of those tubes. If you have them cut perpendicular to the long axis, then they look like pillows, and this is often what we refer to as pillow lavas. Pillow lavas is a feature that forms underwater when the lava quenches against the cold water, and it makes these tubes, and cut in the right way, they look like pillows. In the bottom right-hand image, we have the breakout of one of those pillows. You see a bit of lava breaking out of a former tube. This is when it freezes over, it crusts, and then it pushes a little bit, and then it breaks out again. Then we get these tongues coming out of pillows. So here's a few more of those impressions, submarine volcanoes, and there is one of those challenging sampling missions where you have to break off a rock without breaking the device. And this is how we get samples from the ocean floor that we can analyze chemically. So here's a few more of those impressions, and not surprisingly, this is also a good substrate for all sorts of organisms. And I'm not so familiar with living things. I understand volcanoes better than living creatures. So I can't quite tell you what they are, but we'll come back to living things in a short while. Another really intriguing feature, and this was a little test I did with my students for many years, was when people discovered these pillars in the top of the slide. There's two images of these weird pillars. And initially people were saying, oh, there's drowned cities down there. And all sorts of spectacular claims were made, but I assure you there's no drowned cities there. These are actually also geothermal pipes that have, been forming when there was liquid lava, but the lava then drained away, and where the hydrothermal waters were coming through, the lava got quenched, making these pillars. And the evidence is actually in form of some of these specimens in C and D, because this is a crust, and you see that the crust was inflated and was pulling the lava along. We call it Pellé's hairs when it does this, these really thin streaks, and that can only form in liquid kind of situations, and it's not a man-made feature at all. So we have these rather spectacular pillars down there at the ocean floor in the Rift Valley, when we have lava lakes that partly drain away, but the crust has already formed, then we get features like this. So, coming back to these smokers, they make these chimneys, and they're quite spectacular. They can be very tall, tens of meters, and they usually make fields around them of the fine, dusty material of the precipitate. And in case of the dark ones, this is quite useful because there's a lot of copper, there's a lot of tin, there's a lot of iron in there, and it makes lenses on the ocean floor that are quite enriched in these sulfite minerals. So here's a few more impressions of that. And these are actually places where life thrives. initial research has found all sorts of creatures there. Many of them are familiar to us, but there was also what's known as archaeobacteria, archaea. Actually, I'm told by my biology colleague, it's not really a bacteria, it's more complicated, but let's live with it. I'll call them archaeobacteria now. And these are very simple life forms that live there, and they love to live in really acidic conditions and in very warm conditions. And some people speculate that this could have been the origin of life. So, strangely enough, when there's a new vent forming, people have done research, it actually is a surprisingly short time required before these guys actually show up at these vents. So they migrate. They can survive spells of colder temperature and different acidity, and they can actually colonize new places. So these are quite the survival strategists, I believe, and they are believed to be some of the oldest life forms on the planet. So, now we had a look at the ocean itself. We had a look at these spreading centers. And here in the center of the image in red, there is the one in the Atlantic. There's also one in the Pacific, I said. There's also one in the Indian Ocean. But having talked about the center of the Atlantic, let's look at the margins very briefly. What happens at the margins? Well, not much is the answer. Geologists call them passive margins. So there is not much going on at the margins of the Atlantic. There's no big phenomena. It's not like the ring of fire in the Pacific where we have subduction all around. And subduction actually happens when the ocean crust is a little older. When it's a bit thicker, a bit colder, a bit denser, then it starts to sink down. We haven't reached that stage in the Atlantic yet, and this is why most of the marginal areas are actually just passive margins. Well, passive doesn't mean nothing happens. Every now and then there's landslides, and there was a big landslide about 6,000 years ago when the glaciers melted off Norway, the Storeca landslide. And this is something I'll talk a little bit more in the final part of the presentation. But in red here in the map, there's this large landslide, and it went into the abyssal areas of the Atlantic towards Iceland, and it caused a big splash. It caused a big tsunami, and we have deposits of that tsunami all around northeastern Scotland and also the Shetland Islands and the Orkneys. So this can happen at passive margins, material being shed into the ocean basin. But subduction, I talked about the ring of fire, and a mature ocean, well, produces crust, and it spreads out and it gets subducted at some point. But in the Atlantic, we don't see much of that. There's one point, however, and I mentioned it earlier, it's the deep area of Puerto Rico. This is where we have the first little bit of subduction going on. It started, if you will. So this is the Atlantic, well, becoming a mature ocean. And there we have this island arc, and that's typically a feature of a bit of plate being pushed into the mantle again. And this happens here with about 19 millimeters a year, about 2 centimeters a year, and that's where the ocean crust is really old, the oldest in the entire Atlantic, and this is why it starts to subduct. So there we have these deep trenches when this happens, and this is the Milwaukee Trench. This is 8,500 meters deep, the deepest point in the Atlantic. So I don't want to scare you, but I wanted to bring a scientific diagram. This is kind of on the right-hand side, how scientists want to think about this. And here we see this little island chain at the surface. But we have to realize there's a lot of processes going on. Material is being pushed down, and it causes volcanism at the surface. So, having talked about Iceland, having talked about the spreading, but also the subduction, I should point out that plumes like Hawaii or Iceland are not so rare. They're actually quite common. So in the Atlantic, we have a fair number of them. If you have the chance to go to the Azores or Madeira or Canary Islands, there you also see these features. They're anomalous hot spots that come up, and actually the Atlantic has a fair number of them. So here's a bit of evidence. This is the Canary Islands, and the Canary Islands, they are cutting across the ocean floor magnetic anomalies. The yellow ones in the top right, that's the magnetic anomalies of different ages, and the islands really cut across this. Has little to do with ocean spreading, it's actually to do with these hotspots, and in the lower right, each of those yellow dots is a hotspot, Hawaii being one of the most famous ones, but there's quite a lot of them. And the red lines is the hotspot tracks. It's like a Bunsen burner. When the plate moves, then one island forms after the other, and then sometimes they get submerged or they stay above the ocean, and then we have these island chains. So let's bring the geology together. We have rifts in the center, we have blooms, and we have the first little bit of subduction in the Atlantic as well. And sooner or later, it's going to look like as we see it in the Pacific. So here we have the ring of fire all around the Pacific. We have subduction. So the plate that's made here at the spreading center is taken away again. And right now, we don't see that universally in the Atlantic. But in a few million years, this will happen. So the geological future is very clear. Unfortunately, I will not see too much of it. But there couldn't be a lecture about the Atlantic Ocean without talking about Atlantis. A few words about Atlantis. So, geologist's point of view at least. So, ever so often we see these kind of news, and Atlantis is a feature that's first been described, by Greek philosophers, and it goes back to 450 BC, and it means the Sea of Atlas, or the Atlantic Sea. This is where the term comes from, and it implies that there is a land out there in the Atlantic Sea. So beyond the Pillars of Hercules, there is this magic land, or used to be a magic land. Well, and this disappeared at some point, so people claim, and maybe it's on the ocean floor out there. And artists' impression are quite, colorful. You look at the lower one here. So again, we have drowned cities, and I mentioned drowned cities before. And so people have drawn maps, all sorts of maps, and often Atlantis is actually put into this area here, pretty much where the Azores are. So here, where also the geological triple junction is of the North American plate, the Eurasian plate, and the African plate. And if you look at this diagram down here, or this map, it's a bit confusing because the north arrow is actually pointing towards the bottom. That means America is here on the right, and Africa is actually on the left. And there's always this big peak in the middle. So there is this idea that there is a volcano somewhere in Atlantis. And if you look at various representations of it by various artists and various writers, where very often we see this big volcano there. So in the top here, we see this one here. And I think this has to do with the Azores to some degree, because there is one volcano on the Azores that sticks out, and it's called Pico. And the idea here is that the drowned landmass of Atlantis, only allows the peaks of the highest mountains to stick out. But I assure you that this is a very isolated little island, and we have ocean floor mapping now. It's not a drowned continent, and this just happens to be a nice pointy volcano, and of course, it gives rise to great ideas. So then there was various descriptions of how this wonderful civilization looked like, and if you read all sorts of books, you get, very colorful images here. Personally, I don't think we have much evidence for this kind of thing. However, I believe there is something like Atlantis, but it looks very differently to what people generally tell you. Here, this is one of the tabloids in the UK, and it claims that Atlantis was found. And it turns out that they look at the rock oil trough, which is actually a formation of basaltic rock that forms a plateau underwater. So again, I have to say this is very unlikely that this is Atlantis. And these wonderful diagrams or paintings here, they're no more than artists' ideas. So, and the evidence for that here is that if you look at these rocks here in gray, this is submarine basalts that come from the Icelandic plume, and they go back 60 million years. I talked about it in my previous lecture. And it's not Atlantis, it's a submarine basaltic plateau. However, there is an area that got drowned by the Atlantic, and this is Doggerland. Well, what is Doggerland? There was an entire area between what's nowadays England and the Netherlands and Scandinavia, and that area was actually above sea level some 10,000 years ago. And Doggerland then eventually drowned, and people are finding all sorts of artifacts there and fossils there. A fisherman brought up this mammoth skeleton that I'm showing in the bottom right. So this was land, and creatures did migrate on it. And this got eventually completely drowned by the melting glaciers over the last 10,000 years. And here in red, there's various retreat lines of glaciers in northern Germany and Poland, and all the water had to go somewhere, and it was drowning the areas. So here's a progress of Doggerland, and we're going from left to right. Left is several thousand years ago when the ice was coming down, and then we see how the land was drowning. And at the moment, all there is Doggerbank, a shallow bit where we have not a lot of depth of the ocean, and this is the remaining part of it. By now, people have even found settlements down there, and the final drowning happened about 6,000 years ago. So it is conceivable that legends of it were spread all across Europe, and that could have reached even the Greeks. So my final few points is about treasures, because there is treasures in the Atlantic. They're not linked to Atlantis, but they're linked to the spreading centers we talked about. And I mentioned there's these black smokers, and they make a lot of sulfide minerals, and we need a lot of this in the future. We have vast amount of needs for copper, for example. If we want to electrify the traffic, for instance, copper will be, well, we need to mine a lot more than we're mining right now to satisfy all these wishes, and therefore we might need to go submarine. Let me give you a flavor of this. If you look at a conventional car, this is an American source, so it's in pounds, and here for a conventional car it's about up to 50 pounds of copper that we need. If we want to kind of go towards electric buses or hybrid electric buses, we need hundreds of pounds of copper. Not to mention getting an airplane flying on a battery. So there will be vast amounts of these metals needed, and that's where people want to go. So we form these chimneys down there, and these chimneys sit on lenses, and the idea is that somehow people want to go down there and get this material scooped up. Now, we talked about all the organisms there. It's going to be very unfortunate for those, but on the other side, well, this is an ongoing debate. What happens there is that the cold fluids of the ocean floor, they penetrate via the fractures, they get heated up in the deeper part, and then they dissolve all sorts of metals, zinc, copper, iron, but also manganese, for example. And when the hot water comes up, meets the cold ocean floor, then it precipitates all these metals. So we have a very acidic material coming up at 350 or so degrees, and this brings the metals with it, and so we deposit them locally. And this is one of those layers of the black material there. It's one of those metal layers, very rich also in cobalt. This is also something we need, and this is why people are so keen on these things. Cobalt, I mentioned just a second ago. We have an even bigger problem with cobalt than we have with copper. Right now, most of our cobalt comes from Congo, horrendous conditions. So, but we need the cobalt for making batteries. So there's a lot of efforts. The Dutch government have just released a vast amount of money for research going into submarine mining. So another thing on the ocean floor is manganese nodules. Manganese is the only metal that doesn't precipitate immediately at the ocean ridge. It actually floats in the water for a while, and then it precipitates around rock fragments, and it makes these nodules, and there's entire fields of manganese and cobalt nodules. And this is where the idea comes from, to go down with a big hoover and just hoover them all up. The idea is actually not completely crazy. There was a bunch of pirates off Namibia, and they were realizing that the sand washed off from Namibia's onshore diamond deposits contains diamonds. So they were just going a little bit outside the national boundary, and they hoovered it all up, and De Beers could do nothing. So, and here the idea is, can we hoover them up? Well, I don't know, but there's various ideas about it. It's not a reality at this point, but we have some samples here. We have fragments of rock layered with these crusts, and potentially people could imagine scenarios of remotely controlled diggers and other vehicles, and they could potentially allow to bring that material to the surface. So, deep sea mining for manganese and copper nodules, will it be a reality? I think it will be tried. I'm pretty confident about that. There comes a lot of problems with this, of course, and here is ecosystem problems. And current research states that it's not the macrofauna, it's not the big fish or things like that that are the problem, it's the microfauna. It's the tiny little animals that are living there that we have not considered and that we don't understand in full. And there may even be species we haven't actually even seen. So we might be killing things that we don't even know. So there's a big debate right now, and I usually show this to my students. This is a Greenpeace cartoon, and it says here, what are all these minerals used for? Well, for clean technology, and it's, well, destroying the ocean floor. So there is a bit of a dilemma. I don't have the answers, but this is certainly something we as a society have to deal with. So, and this brings me to an end. I'm a big fan of Jules Verne, and you may remember, you've watched the movie or even read the book, 20,000 Leagues Under the Ocean. Well, Jules Verne was very perceptive. He realized there's big volcanoes under the ocean. He realized that there's a lot of treasure under the ocean. This is how Captain Nemo got so rich. He exploited all the submarine ore deposits, and he realized that we will have to grapple with submarine life sooner or later in a bigger way. The only thing he didn't get right was the size of the submarine life. Thank you very much.